Now we must discuss something about so-called spectral theorem. Spectral theorem. It is something representation or something point of view on self-adjoint operators again. But shortly I can prove only for bounded situation. For unbounded situation I just write some formulation, some analogy statements for unbounded operators. But for bounded operators we can prove something strictly. So the main idea, what is the spectral theorem? Short, in brief, in one sentence. Any self-adjoint operator is operator of multiplication. This is main idea of spectral theorem. But then you must precise multiplication on what and where. Examples. Finite-dimensional situation. Any symmetric matrix in some orthonormal basis can be represented as diagonal matrix. So you have a multiplication on diagonal matrix. Gilbert-Schmidt theorem. We have self-adjoint compact operator in infinite dimensional space, Hilbert space. You can find a basis which consists from the eigenvectors, and your operator is similar to multiplication on diagonal 2, but infinite diagonal. What happens for arbitrary self-adjoint? So self-adjoint operator finite dimensional says diagonal. Compact self-adjoint operators, compact are nearest to the finite dimensional situation. Again, diagonal. Yep. Is it clear what I say with it is diagonal? Because if we have Gilbert-Schmidt theorem, we have self-adjoint operator which is compact in some Hilbert space. Then they exist orthonormal basis which consists from the eigenvectors. It is the same if you say your operator is similar for operator of multiplication of the sequence lambda k in L2 small. Because as it is basis, any vector can be represented as Fourier sum. Yep. And then the action of operator AX equals to you can denote this as xk, Fourier coefficients. And we know that Fourier coefficients lies in L2 small. In L2 small, you have operator B multiplication on these sequences of eigenvalues. Operator A and B are similar. So you have multiplication again on this operator. But we know that compact operator have only point spectrum except 0. 0 can be any spectrum. Not any. If self-adjoint, it can be point spectrum or can be continuous spectrum. Residual spectrum is empty for self-adjoint operator. But if operator is not compact, it's possible that it have no eigenvectors and no eigenvalues. It is possible that point spectrum is empty. For example, consider so-called, how it named in quantum mechanics, operator multiplication on X. Or coordinate operator. Function is continuous, and it is strictly increasing. We prove that for functions, the operator of multiplication on functions, the spectrum is just the values of this function. And if function is constant on some set with positive measure, then it is point spectrum. But this function is strictly monotonic. So there are no sets of constants. So spectrum is pure continuous. only continuous function. What we can say about them? But this is easy situation because this operator just a multiplication of the function, and it will show that a typical situation that any self-adjoint operator is operator of multiplication on some function, real valued function. Real valued function. First, I want to remember one theorem from the spectral theory, so-called the map transforming theorem of spectrum. What it means? Let theorem. We have bounded operator, just forget some about unbounded operator, come back to the bounded operators. And let polynomial. Some polynomial. Then you can define the polynomial of operator. What is the spectrum of this operator? What is the spectrum of this operator? Answer. It is values of this polynomial on all points of spectrum. This is okay, proof. Moreover, you can see that some classification is the same of the spectrum. What we know about polynomial? The main theorem of algebra. It have just yes, in complex plane, but spectrum is the numbers in complex plane. In complex plane, have just n roots up to the multiplicity. So we can represent it as and I think, is it clear what means the polynomial of operator? Yes, ZK is the compositions of operators, the powers of operators. And A in zero power is identity. So, first, let lambda in spectrum of P of A. What means it? This means P of A minus lambda identity equals A minus lambda 1, etc. A minus lambda A identity. Yes? It's just all Z substitute on operator. It just means the spectrum of polynomial of on operator. So if lambda belongs to the spectrum of operator P of A, then this operator is not invertible. Yes? It means that there exists some operator here which is not invertible. Because if all these operators are invertible, the composition of invertible operator is invertible operator, yes? And invertible of composition is the composition in back order of inverse operators. So exist I such that is not invertible for some I. Yeah? What can we do further? Following. We know that this operator is not invertible in maybe different situations. Yes, it may be not injective, for example. If it is not, but all this, is it clear that all these factors are commutates with each other? Because A is commutates with A. Identity commutates with any operator. Because it is commutates, so if A lambda I is not injective, how we can write this product? How we can write this product? In this way, A n G is not equal to I, A minus lambda G identity, and the last operator A minus lambda I. I put it on the first place. I can do it because they are commutative. Then what you can say about I think it is second part. It is not invertible. It is sufficient. Then I prove another. Here I just begin proving another statement, another inclusion. But stop. Come back to this. If it is not invertible, then lambda I belongs to what? To the spectrum. Okay. To the spectrum of operator A. But and this is zero, because it is zero of this element. So what we obtain? Lambda equals to P of lambda E. So what is its inclusion? We suppose that lambda is from the spectrum of operator P of A. Yes? And then we show that this lambda equals to value of polynomial of our polynomial P on some point from the spectrum of operator A. So we show that this belongs to the of this. Yes? We show this inclusion. The value lambda equals to value of a polynomial on some point. Second, so let's lambda equals to this. But by this decomposition, we can obtain that this lambda equals for some lambda I belongs to the spectrum of operator A. Yes, by definition. And and we see that lambda I is the zero of our polynomial. Yes? So it's just lambda I is from these numbers. So we have that some exists. So some for factor with lambda I, operator A minus lambda I is not invertible. By the way, one remark. there is examples of operator which are not invertible and not commutative, and its composition is invertible. Shift to the right, shift to the left in L2 small. The composition is identity. It is invertible. But shift to the right is not invertible. Shift to the left is not invertible. But this operator is not commutative. And this operator are commutative. So what my arguments, which I begin before, if it is not invertible, if lambda I is from the point spectrum of operator A, I write P of I minus lambda I as AN, then product for G which are not equal to I minus lambda GI, and I minus lambda I put on the first place. And if it is from the point spectrum, what we have? We have that there exists X which is not 0 such that A minus lambda I X equals to 0. Then we immediately obtain that P of I minus lambda E I X equals to what? You act by first operator on X, you obtain 0. All operators are linear and 0 goes to 0. So we immediately obtain that 0. So here we see that lambda in spectrum, moreover, it is in point spectrum. So again, I take lambda equals to value of polynomial on spectrum, and we show that this lambda lies in the spectrum of P of A. Moreover, in the same. If lambda I belongs to continuous spectrum of operator or in residual spectrum of operator, what we know? We know that operators are injective. Yeah? We know the operators is injective, but the range of operator is not space, is not all space. Yeah? So what we do? Write our operator in such way. Here G. I put it on the last place. These operators do something with our space H, X. We work in Banach space. But last operators, the range of operator is not all space. Yes? What you can say about the range of this operator? This operator spoiled the range. So the range of whole factor of whole product is not all space. So lambda belongs to the or continuous or residual spectrum of operator P of A for this operator. So it is in spectrum again. So we prove another inclusion. Some examples of application for this theorem. For example, you have self-adjoint operator, and you know that the spectrum of this operator is 2 points, 0 and 1. Proof that it is projector. Can you prove that this then operator is projection? But this is important. This is important. What you say? It is important that operator self-adjoint. If it is not self-adjoint, it is not true. It is not a projection. Maybe. Maybe projection, maybe not. maybe not. You can consider, for example, Jordan blocks with the zeros on diagonal and with 1 on diagonal. Then spectrum is 1 and 0, but it is not a projection. Use this theorem. Try to construct something polynomial. What polynomial? Not. I construct just a polynomial with zeros on spectrum. What you can say about by theorem of transforming of what is the spectrum of this polynomial? It is P of spectrum, and it is 0 because the spectrum is 0 of this polynomial. So the spectrum of this operator is 0. But this operator equals to a square minus a. The coefficients of the polynomial is real, so it is self-adjoint operator. And we know that for self-adjoint operator, spectral radius equals to what? To the norm. But from this, what you can say about the spectral radius of this operator? Spectrum have only one point. So spectral radius of operator P of A equals to 0. And it is equals to the norm of operator P of A. For self-adjoint operator, spectral radius coincide with the norm. So you obtain that the norm of this operator is 0. So a square equals to a. And what is the definition of projector? Just this definition of projector. If the square of operator coincides with operator, it is a projection. Okay. Moreover, is it clear that we can, if you have a polynomial, you can define the polynomial of operator for any bounded operator? Yeah? As a composition. So if we have an abstract polynomial, and we have bounded operator, maybe in Banach space, we can define P of A just by the rule changing the variable z on operator A. And additionally, I write that 0 power is an identity operator. Further, but for many applications, the set of polynomials is insufficient. It is interesting for some applications to define more wider class of functions. For idea of spectral theorem is try to define for some function f. For arbitrary it is impossible. But it is possible. For example, if you take analytic function, so it can be represented as series, and if its series converge on the set wider than spectrum, then you can define why wider the spectrum, because spectrum lies inside this ball with radius norm of operator. Then of course the series converges. So we can define exponent of operators, for example, sine of operator, cosine of operator, for any bounded operator. Moreover, exponent, sine, and cosine analytic function in whole space. So you can define for all bounded operators. But again, for some applications, analytic functions is of narrow class. So for some applications, we need to define, for example, for continuous function. Can we define you have operator and you have continuous function on operator, on the spectrum. On the spectrum. Can you define the function of operator? For example, logarithm of operator, the absolute value of operator, square root of operator. For some, yes, of course, because again, I can repeat, for example, Hilbert-Schmidt theorem. Hilbert-Schmidt theorem, you have self-adjoint operator, and it is compact. So again, we know that there exist orthonormal bases which consist from the eigenvectors. What it means? Because it is basis, you can represent any vector as Fourier series, and operator A works as. And now imagine that function f is continuous on some set. I write it as following. It is continuous on lambda k. Can you define the function of operator? Of course, this set for compact operator is bounded, yes? The largest number, absolute value of the largest numbers, the largest absolute value is the norm of operator. So it is bounded set. Continuous function bounded set is bounded. Fourier coefficients lies in L2, so of course this series is converged. And this is well defined because we take function which is continuous on this set. So for example, for self-adjoint compact operators, you can define the function of operator if you can define function f on this set. Now, let's formulate and prove the theorem on the so-called continuous functional calculus. We have self-adjoint bounded operator. Then there exists unique homomorphism from algebra of continuous function. All continuous function on the interval is an algebra. It is linear subspace. It is group for addition and semi-group for multiplication. So it is algebra. It is a ring with the structure of linear space. And all bounded operators is algebra too. It is linear subspace with and it is ring. Ring. Semi-group, you have a composition, but you have no inverse element. For multiplication, we know that there exist not invertible operators. But in some, it is group. Because in some, for any operator, you have an inverse operator minus A. And 0 as unity. But multiplication, it is only semi-group. It is only semi-group. So it is a ring. Homomorphism phi. Let's define it by letter. And it is then later remark with properties. First, phi is it clear this writing? If I write just, is it will be understand or not? X is not abstract element, it is just a variable. I write f of x, function f of x equals to x. These functions go to a. And this function is identity. So f constant 1. These functions go to I, these functions go to a. Third, phi alpha f plus beta g equals alpha phi f plus beta phi of g. Phi of f multiplied g equals to phi of f multiplied phi of g. Fourth property. If fn converges to f uniformly on AB, then phi fn converges phi of f in norm of this space. Moreover, the norm of phi of f less than maximum of phi x for additional property for the 5. The value of this homomorphism on the conjugate function is a joint operator. And the last 6, if BA equals AB, then phi f B equals B phi f for any continuous function, for any f CAB. If some operator commutates with A, then the result of our homomorphism with function f, of course, commutates with the same operator B. So then you can define the phi of f is just f of A. Then we take the function of operator is just a result of this homomorphism. Homomorphism make a correspondence between function and operators. And then we divide the function of operators as just a result of this homomorphism on function f. Okay? Is the formulation clear or not?
It's not an isomorphism.
No, it is only homomorphism. Only homomorphism.
Okay.
Just property 3 is just definition of homomorphism of algebra. Yes, it's just a definition of homomorphism. It is algebras, so it is a homomorphism of linear subspaces, and it is homomorphism of compositions. We can define the composition of functions, then we can define the composition of operators.
Could you repeat it? 0.5 because I.
0.5555. The result on conjugated complex conjugated function is the joint operator.
Okay, thank you.
It is a joint operator. So by this theorem you can define the function of operator. Just this is the definition. How you can define the function of operator? It is a result of this homomorphism on this function. Only demand that function must be continuous on the spectrum. Moreover, you can consider not this space, continuous function of the interval with the properties that spectrum of operator lies in this interval. You can consider continuous function of the spectrum. But spectrum can be very difficult constructed set. So it's more easy to consider more convenient space, continuous function on the interval, but the main demand that the spectrum lies in this. So, proof. First and second property automatically defined your homomorphism on what functions? On polynomial, yeah. From 1 and 2, we have phi of if p equals a k z k is polynomial, then we automatically obtain that phi of p is yes? Because identity 1 goes to I, then we have property of homomorphism, so coefficients lies here, and then we have the powers of operator A. So on polynomial we have a good definition, and it is unique, of course, yes? It is only by the assumptions of the theorem. We want this property of homomorphism. It must on polynomial give a polynomial of operator. And this is just a definition of homomorphism, I repeat. So what we can take with arbitrary function, which is continuous on the spectrum or on whole interval. Weierstrass theorem, what gives us? So for any f which is continuous on the interval AB, and AB contains the spectrum, what I take? Weierstrass theorem says that there exists sequence of polynomials which converge to our function f uniformly. Uniformly. Good. What you can say about this operator? Just like the norm. If all coefficients of polynomial are real, this operator is of all polynomials Pn are real, this is self-adjoint operator, of course. But if coefficients are not real, it is not self-adjoint operator. But our operator is self-adjoint. So operator A commutates with itself, yes? So it is normal operator. Normal operator. I don't remember, have we such problem? We prove that the spectral radius for self-adjoint operator coincide with the norm. But have we task that for normal operator, the spectral radius is coincide with the norm too? No, so it will be today in homework. So for normal operators, spectral radius coincide with the norm. So it is spectral radius of this polynomial, of this operator. By definition, spectral radius is what? Maximum lambda in spectrum. Yeah? So it is maximum lambda in spectrum of yes? And now use the theorem on transforming of the spectrum. Previous theorem, yes. What is the spectrum of polynomial? We prove it for any bounded operator. So it equals yes. The spectrum of this operator is just value of polynomial on the spectrum. It is, of course, less or equal on the interval, because we have this assumption that our interval contains the spectrum. If you want to consider this property, you can consider continuous function just on spectrum. In this situation, this is equality, yes? But here we have a wider set, so it is an equality. But this goes to the zero by this theorem, Weierstrass theorem. Any continuous function can be uniformly approximated by polynomials. We must, so this set of operators is fundamental. You see. Pn of A is fundamental. So what you can say? Exist limit let's define this limit as function of operator. So we have a possibility to obtain the function of operator. The main thing, function must be continuous on spectrum. But what we must check in this approach? Here one problem. It is not. It is less or equal to the function. By this equality is less or equal to the uniqueness. It is less or equal to the normal function f. Function f on bounded interval is. So this is approach impossible for unbounded operators. Yeah. Because there is a problem for unbounded operators. But what we do for unbounded operators? We have unbounded self-adjoint operator. We have Cayley transform. The Cayley transform is unitary operator. It is bounded. So you can define the polynomial for unitary operators. Unitary calculus, and then you continue again this unitary calculus on continuous function. And then come back to the self-adjoint operator with an inverse Cayley transform. This is idea for unbounded operators. But for unbounded operators, it's not bounded, yeah, of course. Maybe bounded, maybe not. It depends on function f. Uniqueness. Because in Weierstrass theorem, this sequence is not unique. You can imagine a lot of different sequences of polynomials. Why they have the same limit? Why this definition is correct? It is easy because we have standard methods by interlacing of two elements of two sequences. So if Qn, some another sequence of polynomials converge approximates f, what we can do? We construct interlaced sequence. P1, Q1, Pn, P2, Q2, etc., Pn, Qn. It's converged to f. Yes? And as we show, then interlaced sequence of operators, Paa, Qaa, P2a, Q to A, etc. Pna, Qna is fundamental. So interlaced sequence is fundamental. So what you can say about the limit? The same. So limits are the same, so this definition is correct. This definition is correct. And other other properties of our homomorphism is automatically. So we obtain this situation. If functions converge uniformly, then we obtain that operators converge in norm. Yes? You can take it with the help of polynomials, for example. And for polynomials, a joint polynomial is just this polynomial. I consider polynomial of the real, on the real axis, because spectrum lies on the real axis of self-adjoint operator. So that is a real value variable. And then conjugate AK, and you see that it is just this operator by the rule of conjugation of the sum of operators and composition of linear combination of operators. Operator A is self-adjoint. It is functional. It is continuous functional calculus for self-adjoint operator. And if it is P of A, so it is true for polynomials. Any continuous function can be approximated by polynomial, so as a limit we obtain this property for what? For functions. So as a limit we immediately obtain that for functions f phi, the result of homomorphism is just this. Because it is true for polynomial, and any continuous function phi can be approximated by polynomial. And conjugated function is approximated by conjugated polynomials. And the last property is easy, because if operator B commutates with A, it's commutate with any polynomial. If BA equals AB, that P of A B commutates with the polynomial of operator. And again, as a limit, any continuous function can be approximated by polynomial, so we obtain that this rule is valid for the continuous function. Yes? As a limit. As a limit, because any continuous function can be approximated. So we obtain continuous functional calculus. We can define the continuous function of operator. But function must be continuous on the spectrum.
You said we can define the continuous function of operator.
Continuous function of operator, yeah.
This homomorphism with not bijection.
No, it's not a bijection.
And how, if I have an operator,
but we don't know, we do not need a bijection. If you have a continuous function, you can define the function of operator.
Yes.
Our idea was from any function from this set, which contains spectrum of operator, to define f of A.
Yes, okay.
So it is homomorphism. There are a lot of functions which is not, operator A is given. One given self-adjoint operator. You can define the polynomial of operator, you can define sign of operator, exponent of operator, but you can define any continuous function if this function is continuous on the spectrum by this theorem. definition as we take this definition. But in verse we don't state that it is a bijection, it is not correct. So why we must prove incorrect statement? So we have no inverse maps. So it's clear, yeah? But again, for some applications, we need more wider class than continuous functions. So the next class will be Borel bounded functions. I consider functions which works here, real functions. For complex functions, you can consider apart the real part of functions and imaginary part of functions. Yes, the function is measurable if for any constant real Lebesgue. Measurable belongs to the measurable by Lebesgue. And is it clear that all such semi-axes arise all open sets? So it is the same as preimage of any open set. But any open set generates a so-called Borel sigma algebra. Borel sigma algebra is the minimum sigma algebra which contains all open sets. Sigma algebra is a class of sets for which you can do anything. Union, intersection, incountable numbers. You can consider countable intersects and countable unions. And it again belongs to the sigma algebra. So you can rewrite this definition as preimage of any Borel set, but Borel set is the again Borel sigma algebra. Borel set is sets which generates it's minimal sigma algebra which contains all open sets. By this semi-axis you can obtain any semi-set, any open set. On real axis, any open set is a finite or countable union of intervals. Intersections of axis to the right, semi-axis to the right, and semi-axis to the left. It is interval. It is just an interval. So the equivalent definition of measurable functions, preimage of any Borel set, is measurable in Lebesgue. But Borel functions, preimage of Borel set is Borel set. That's all. And what is the difference between Borel sigma algebra and Lebesgue sigma algebra? Any set from Lebesgue sigma algebra can be represented as set from Borel sigma algebra union with some set with measure zero. And on integrals, when we integrate it, the sets of zero measure doesn't include an integral. So it's sufficient to consider Lebesgue integral only on Borel sets. So it's sufficient to consider Borel functions. So Borel functions is something unknown thing, yes. But definition, the preimage of Borel set is Borel set. So, okay. Some B, what is I write it. So Borel set on interval AB is minimum sigma algebra which contains all open set from AB.
All open set are like the generators of these algebra.
Yes,
Okay.
yes, yes. You can define it as sigma algebra which generates, it is just the Ford's minimal sigma algebra, the same words. And F Borel functions it is full preimage. Full preimage. So all X, this is what means. Here A is not operator, here is a okay, then when I tell it's on the level of only of ideas. Theorem 2. Borel bounded functional calculus. So here we can define, on previous theorem, we can define continuous function of operator. And by this theorem, we can define Borel function of operator. Borel bounded functions on interval which contains the spectrum of operator. So let A is self-adjoint, A is bounded operator, and interval AB contains the spectrum of operator. Then it is I write it as definition of Borel set. How I can write the definition of Borel functions?
The inverse image of a Borel set.
This is by this symbol I define. I know the Borel set. Okay, there exists unique homomorphism phi from. I write here Borel functions. Here 1b is Borel set and Bor is Borel functions. Okay. It is the same, yeah, as in previous theorem. Because we need the uniqueness on the polynomial, yes, and we need the rules of homomorphism. But fourth is not true. If for continuous functions, what converges is natural for continuous functions on the interval. We want the space will be complete, is uniform convergence. For Borel functions, the natural convergence is pointwise convergence. Pointwise. So if Fn x converges to Fx for any x lies in AB, then phi fn strongly operator convergence. For continuous function, we have non-convergence for operators. For Borel functions, we have only strong, so again pointwise. So actually on each vector. But and 5 and 6 rule are the same. 5 property of this. The homomorphism on conjugate functions gives us the adjoint operator, and 6, if AB equals to BA, if operator B commutates with A, then phi F B only idea how we can prove it. Let's have continuous functions. X and Y fixed elements in H. Consider this scalar product. It is number. X and Y fixed. A is given for us self-adjoint operator. What we can change in this scalar product?
Prove that we can switch the order?
No. We can take an arbitrary function f. Is it a linear functional on continuous functional f? Yes? It is continuous functional. On f. Because by Cauchy-Bonnikovsky, the absolute value by first theorem, we know that the norm of this operator less of this on AB. T, yes, T, X and Y. X is an element in Hilbert space, so function of ft. We know that the norm of this operator, we show it, less or equal to the maximum of function. So it is a bounded functional, yes? And of course it is linear functional. Remind the theorem on description of all continuous functions in space of continuous functions. Theorem on continuous functionals on space of a continuous function.
It was the value in one point.
Hmm?
Was the value of the function in one point?
No,
No?
no. It is only one example of such. The theorem was another. It was about October or November.
Our product.
No scalar product. The last attempt. How looks like arbitrary functional in space of continuous functions.
Is an integral.
Yes,
It's an integral.
integral. So there exist functions g of BV0 on AB.
Yes.
That this functional Of course, this function depends on that x and y. Of course, it depends. And now we can approximate any bounded Borel functions by sequence of continuous functions. Then if we take now f from the Borel functions AB, then there exist fn, which is continuous functions, and fnt converge to the f, point-wise convergence. You can consider this as not functions BV0. You can consider this integral as integral on some Borel measure. dg generates some Borel measure. So you can use all good theorems for convergence of integrals. So if you consider bounded Borel functions, then this sequence will be bounded. By Lebesgue theorem, Lebesgue limit theorem, it will be converged that integral fn dg converge to nf dg. And here you have fna scalar product xy equals to this. Yes? These converge, so we have here weak convergence, not strong but weak convergence, to some operator B, to the semi-square form of some operator B. Of course, here will be something linear dependence, yes, because this linear operator, and this linear operator. Integral is linear. So here some linear operator. Integral of linear combination of functions, it is linear combinations of integrals. So it is some linear dependence to the right, so we have linear dependence to the left. So we obtain that, then we define phi of f as this operator B as limit of f and a. But what limit? Here, just a weak operator convergence in Hilbert space. Not strong, but weak. Weak operator convergence. So we define this operator B. So f and a converge weakly to some operator B. But due to self-adjointness, you can change it to the strong. Why? Why you can change it to the strong? If you consider conjugate function, of course it converges to the square, yes? Then you obtain that fn a star fna converge to the f a square. And this is weakly converged, yes? But weakly converged in Hilbert space for any x and y. Just for any x, fna star, fna, scalar products ends on x, goes to the
It's self-adjoint?
yeah, well, it's all operator A is self-adjoint.
Yeah.
It is functional calculus for self-adjoint operators.
So if it's self-adjoint, can you consider that maybe this
We have these properties that result homomorphism on conjugate functions gives us a adjoint operator. Because it is for polynomial true. And as a limit for any function is true.
So can we say that the adjoint operator is the operator itself since it's self-adjoint?
What?
Can we say that the adjoint operator is the operator itself since it's self-adjoint?
No. The function can be complex valued. If function is real valued, this operator is self-adjoint. But function can be not real values. In this situation, the conjugation is important. It gives us different. For example, function fx equals to x, by homomorphism we obtain operator A. But function fx equals ix is operator imaginary unit on A, and this operator is not self-adjoint. It is not self-adjoint. But I finished here. By definition, what you say, you can put this operator on this. And this is just fn ax square goes to fax square. And this is what is convergence?
It's symmetrical.
It's a strong convergence. It's just on the elements. Or just on elements. It is the same, you can write it's fna minus fa x goes to the 0. It's just a strong convergence.
Sir, would you mind just this step? How did we move from this one to this one?
What?
How is this product equal to the modulus of mna x squared?
You put this operator here.
Yes.
And it is fn on a square of the norm. You put these adjoint operators here.
Yes.
fnax, fnax.
Yes.
So it is fnax square. But it is more convenient to consider not this, but minus and go to the 0. Then minus weak convergence to the 0. And minus here the same, and then you obtain this.
Yes.
And this is just a strong convergence. It is just a strong convergence. So we obtain a strong convergence. But other properties of this homomorphism are proved the same way as in the previous theorem. It's a continuous function for continuous calculus. But why we need a Borel functions? Why we need a Borel functions? With Borel functions we can that's Borel set. Then we have a characteristic function or indicator of t equals 1 if t equals to omega, 0 if t not belongs to omega. It is bounded Borel functions. By this homomorphism, you can define this function on operator. What is the class of these operators? What you can say about this operator? For example, if two sets are disjoint, what is it? No. He omega 1 disjoint omega 2 is just he omega 1 plus he omega 2. Yes? So it is, let's define it as E omega. So by this property and property of homomorphism, you immediately obtain it is additive function of sets. But it is not a real valued function. It is operator valued function because it is operator. But it is additive function. It is a measure. In the sense of measure, it is additive function. It is a measure. Operator valued. Operator valued. What you know about the square of characteristic function? It is the same. So you immediately obtain that it is by homomorphism for operators we have the same property. So it is projection.
Isn't this a property of projectors?
It is because of the definition of projection. Projection is operator which is square is coincide with. So it is a projections. And the last thing, it is real valued function. It is a real valued function. So the joint operator is the same. So it is orthogonal projections. It is orthogonal projections. But what we can do with measures? We can construct integrals. Lebesgue-Stieltjes integral. For Borel functions or for continuous function, we can describe Riemann-Stieltjes functions. Then we of course, it is Borel set. For shortness, I define this operator as following. Again, the main property here, it is measure. It is measure. And so you can define just operator A integral on spectrum. And f of A you have an integral representation of self-adjoint operator, of the function of self-adjoint operator. And the definitions of these integrals are the same as for number-valued function. For usual measure, you write the integral sums, but you write these operators and consider the limits. The same construction. For example, if function real. Do you remember the construction of the Riemann integral? Do you remember the construction of Riemann integral? So if function f is continuous, you construct this function f xi and consider take the limit as difference. So you have interval AB, which contains spectrum of operator. You divide it on small subintervals. Partition of this. Consider partition of this interval. Take the middle point xi I, and consider this integral sum, and consider the limits. Because due to these are orthogonal projectors, integral converges in uniform convergence and norm convergence. And if f is Borel function, you consider not Riemann construction, you consider Lebesgue construction, Lebesgue integral. Here, not these times. You consider like integrals for f is Borel functions, Borel on AB. So you consider some f k to n these sums. Here we take the measures, so you take this operator valued measure. And this set is measurable because it is a measurable set. It's Borel function. And consider the limits of these sets. Idea is clear. Because technical proofs of convergence of these integrals is no technique. So I just give two examples of this set. of this so-called spectral function or decomposition of unit, this set of projections named of decomposition of unit or spectral function of operator. For example, of course, they are real because we considered self-adjoint operator. How looks like his spectral function, E lambda? We know that this is equals by theorem, it equals to the integral. But if we have diagonal representation, it is self-adjoint operator, we knows what we knows. We knows that it is sum, so A x equals where EK orthonormal basis. Yes? Self-adjoint operator can be represented as diagonal operator in some orthonormal basis. So the any x is sum, and result of operator A on x is just the sum. So this must coincide with this. So your integral change to the sum. What you can say about this measure? And what you can say about these terms? What is it? Remember linear algebra. One-dimensional projection. How it looks like on line. One-dimensional projection on the line. What is it? You take the vector on this line with the normalized vector. So if you have L, and here E1. So, and you have some vector x. What is this projection on this line? It is, for this, if you take this vector, the projection is like this scalar product, x with A1 and E1. So it is sum of projections. On what? On eigenspace.
It's an eigenvalue.
Yeah. So you can write, I think you know how to draw the graphics of functions. Now you can draw the graph of operator valued function. Here lambda, here E lambda. When we have before first eigenvalue, our characteristic functions is 0. Yes, Borel. On spectrum it is 0. This point contains no 0. And function E lambda is characteristic function of operator A. So it is 0. Then we go from the first eigenvalues. See here, this integral change to the sum. So our measure is atomic measure. Atomic measure, it supports its points. Yes, in eigenvalues. And the jump is a projection. It's just a projection. So here we have P1. P1 on x is x E1, E1. And so on. And after last function point in spectrum, we have sum of all projections, of course it is identity. Of course it is identity. So integral of E lambda whole spectrum gives us identity. But it is easier thing. It is discrete spectrum. Yes, it is point spectrum. How we can describe this function, E lambda is function is not if we have no point spectrum. For example, let's consider another example. Another example. Phi is continuous function, and phi, of course, is a real valued function. Continuity is for simplicity. Of course, in L2 we can consider multiplication on L infinity. So I want to consider operator of multiplication on function phi. And let is strongly increasing. If it is strongly increasing, what is the spectrum of this operator? We consider this operator in L2, of course, in Hilbert situation. Hilbert situation, and it is self-adjoint operator. It is continuous. It is a pure continuous spectrum. Yes, because strictly increasing functions have no intervals of constants. So the spectrum of this operator is phi of A, phi of B. Yes? And E lambda is phi minus infinity lambda of operator A. It is identity if t less than 0 is t less than lambda. Yes, and this identity is yes, because this function of t equals 0 if t less than lambda and 1 if t less than lambda. So we have by homomorphism you have this. So it is a projection on some part. On what part? Let's give a picture. This is just a spectrum. So you take lambda from the spectrum, and you have projection on this part. So E lambda f of x is you see this preimage. This point is phi minus I lambda. And you have projection of your functions on this set. Here your works as identity. And here is 0. So it is example of this function for continuous spectrum. And self-adjoint operator have no residual spectrum, so it's, all spectrum is combination of point spectrum and continuous spectrum. And then you can combine any pictures for spectrum. Well, let's some homework. We have no time, I think. I just today use this property. We prove it for self-adjoint operator, but it is true for normal operators. Try to understand what is function E lambda for this operator. It exists for any self-adjoint operator. Because it's defined from Borel calculus. From Borel calculus. So that's all for today, I think.
What we have to do in the first question?
Find this. For example, I write it for these functions. For strictly increasing function, this is answer. For any strictly increasing function phi. Here is not increasing function, but it is decreasing on half interval first, and it is increasing on the second, and you can combine it. Spoiler, draw the picture for x squared. But first you must understand what is the spectrum of operator. And then write the projection from the spectrum on the values of function. That's all.
Can you say this is kind of a part of the answer from 0 to 1? Or it's so different?
So this function is not zero only on spectrum. Because we prove the theorems for functional calculus on the functions, in continuous function on the spectrum, or Borel functions on the spectrum. And if function is not defined on spectrum, their homomorphism is zero. Is zero. It's defined on, so if we have no points in spectrum, then the result is zero. So for any lambda from this set, we have a zero. But when we goes by spectrum, we must take the largest and the largest set of projections. And when we go to the whole spectrum, of course, we obtain identity, as here. As here.